Good morning, everybody. Yeah, there we go. My name is Mark Russinovich. I'm Chief Technology Officer of Azure, and it's really thrilling to see all the people here for a 500-level session. They wouldn't let me put 500 in, but this is really what it is. It's 400, and the reason is it's quantum computing. Yeah. So it's a lot more technical than any kind of PowerShell session you might go to. So let's talk about what we're going to cover this morning in 75 minutes. I don't hope to make you quantum computing experts, but what I do want to do is introduce you to the world of quantum mechanics and then the basics of quantum computing so you get an idea of exactly what the whole effort that we're undertaking and the industry at large is going after and why it's so exciting and kind of give you a view into the progress along the journey that we're on to really create a scalable quantum computer. And some of the things that we're also doing today to take advantage of some of the learnings that we've got from looking at quantum computing. So first I want to just talk about why quantum computing. And you might have seen some of the motivations for this in Satya's keynote, but one of the very specific problems that quantum computing is promising to give us an answer to is fertilizing the planets. If you take a look at, oh, well, it'd be helpful if I put your slides up. If you take a look at, actually, here's the agenda slide that I skipped over. But why quantum computing basics. I'm going to tell you about quantum computing applications. And like I said, I'll take you into what it takes to build a quantum computer, where we're on that path, and then finally conclude with a look at some of the ways that we're leveraging quantum today to solve problems today, even though we don't have quantum computers. But as I was saying, one of the very exciting kind of problems that quantum computing looks to be able to solve is one related to fertilizing the plants that are used to feed the planet. If you take a look at fertilizer, of course, manure is a common fertilizer, and one of the key ingredients, the key ingredient for plants to grow is nitrogen. Now, it turns out that using lots of cows to produce manure is pretty inefficient. So back in 1910, Haber and Bosch came up with a way to produce artificial fertilizer by creating ammonia, because ammonia has nitrogen in it that can be broken down by plants. Ammonia can be broken down by plants and to yield the nitrogen they need to grow. The problem, though, with the way that we're creating these artificial fertilizers that are ammonia-based is that the process to do so is incredibly energy intensive. In fact, it's estimated that about 3% of the world's energy goes to creating this fertilizer. And it's done at extremely high temperatures, 400 degrees Fahrenheit, 200 atmospheres, so it's incredibly inefficient. Now, the fact is that plants, beans, produce fertilizer themselves. So they produce this fertilizer using nitrogenase, this enzyme right here, which is a protein that plants can use to extract the nitrogen out efficiently. The challenge is that we have no idea how to produce this enzyme. It's an incredibly complicated molecule, and we estimate that it would take about 170 qubits to produce it. It would take millions of years on a classical computer to model this enzyme, but with 170 qubits and a few hundred seconds, we think we could crack the structure of this thing, and then we'd be able to create it artificially. And this is kind of the problem that is one of those, once you solve it, it's solved. So fertilizer is one of those quantum problems. Once we solve it, we now have this very efficient way to fertilize the plants in our food supply. So that's just one exciting example of how quantum can help us. Now imagine all of these other types of problems that we can apply quantum to. Everything from nitrogen fixation, which is what I was just telling you about, to carbon capture, to help address global warming, to material science, to machine learning, to pharmaceuticals, to basically anything where there's an optimization problem where you can achieve quadratic speed up using the elements of quantum computing that I'm going to introduce to you is a potential area where we can use quantum. Now, one thing that want to get to is why quantum computing? Why is quantum computing able to solve a problem like nitrogen fixation in a way that a classical computer can't, that would take classical computer millions or billions of years to do it? And the answer boils down to some of the basic properties of quantum mechanics that we take advantage of with a computational model on top of them. And I want to show you an example live of quantum mechanics in effect. And this is one of those things where I've really gotten passionate about quantum computing personally, because when I started to understand quantum mechanics and the behaviors, the bizarre behaviors that exist at the quantum level, my mind was blown. And so what I want to do, one of my goals, is to blow your mind with the same thing. And this is one of those things that I can't believe that I went all through elementary school, high school, college, master's program, PhD, and I never ran into quantum mechanics that, in this way that kind of blows my mind today as I've understood it. So I'm going to show you an experiment. It's called the double-slit quantum eraser. And before I show it to you live, I'm going to explain with a graphic exactly what we're going to take a look at. So we've got a laser, and that laser is going to send a beam of light through two slits, slightly spread apart. Those two beams of light then are going to shine onto a target. The target is going to be over here, this little piece of paper, basically cardboard over there. And what you're going to see on that is that the two beams go through those slits and cause an interference pattern on that measurement device there. And that's effectively a measurement device because we're looking at what happens to the photons as they go through those two slits. And they act like waves, obviously. And those waves have places where they interfere constructively and places where they interfere destructively. And so this is why you've got this kind of wave pattern of different stripes of intensity. The amazing thing about it is if you put polarizers in front of those two different paths, you put a horizontal polarizer over one, a vertical polarizer over the other, the interference pattern disappears. It's effectively because those polarizers are allowing you to measure which photons go through one path versus one slit versus the other slit. And this is kind of the mind-blowing thing about quantum mechanics, is that the photons travel everywhere until you measure and to try to determine where they went. And then they decide where they went, effectively. And then they boil down to particle-like behavior. And so the interference pattern goes away. Now, the more mind-blowing thing about this is if you put a 45-degree polarizer in front of that the interference pattern comes back. And that's because you've erased the information about which polarizer the light went through. With the 45-degree polarizer on top of that, you can't tell anymore, and you've effectively erased that measurement. Mind blown yet? And now let's see that in action. And here's just another look at that. But let's take a look at it live here. So I've got it as this laser. And the laser is going through a 45-degree polarizer. Now what I want to do is, like I said, take this double slit. I'm going to put this laser through a double slit. And now you're going to see the interference pattern show up because it's acting like waves going through those two slits. Oh, I think I'm supposed to, sorry, change it to camera. So you see the interference pattern? It's light acting as waves. Now I've got this other film here. It's the same two double slits, except over one of them there's a horizontal polarizer, and over one of them there's a vertical polarizer. So I'm going to and now the interference pattern's gone, as we'd expect, because now we've erased which path. Now I'm going to put this other 45-degree polarizer in front of that, and the interference pattern's back. See that? It's a little bit faded because the polarizers cause loss of photons on the way through, but you can see that we've just erased the which way information that came from those intermediate polarizers. Okay, thanks. Now the cameraman, thanks. All right, we can turn back to the presentation now. And you want your mind blown just a little bit more, is if you send one photon at a time and you don't measure which path it's going, you see the interference pattern show up if you've got photon detector on that film right there, detect where those photons are hitting. So in effect, the photons are coming through, but you haven't been able to tell which path they took, so they act like waves, even though there's no other photons for it to interfere with. It's effectively interfering with itself. So you could, if we did that same experiment, we had that laser just pulse one photon at a time, it would have behaved the exact same way that we just saw with the detector on that other side. So that's kind of the mind-blowing effects of quantum mechanics. And there's even more that I've got coming for you in a minute here. Here's another way to look at that experiment. This is called Wheeler's delayed choice experiment. This is a physicist that kind of had a thought experiment. He said, wait, if there's a quasar on the other side of the universe and there's a galaxy in between, we're going to have light bend around that galaxy from the gravity of that galaxy. And if you've got a telescope positioned to point at one side of that galaxy and another telescope to position at the other side, and they're measuring which ones are detecting pulses coming from, or photons coming from that quasar, you've effectively done what we just did with the polarizers of detecting which path the photons taken. So you've done a which way here. Now the mind-blowing thing is if you put a beam splitter and a mirror there so that you cause those photon streams from the quasar to meet, you're going to see constructive and destructive interference show up as if they were acting like waves. Because what you've done effectively at that point is erase the which way information. The photon way back, potentially millions of years ago, it looks like it's decided way back then whether to behave like a photon or a wave based on what you've done on the receiving side. And so this is just another kind of extreme mind-bending view of that which way quantum eraser experiment we just looked at. Now, how many of you heard of Schrödinger's cat? So quite a few of you. And this kind of the same behavior that you're seeing there, where there's a radioactive isotope sitting in a box with the cat, and there's a Geiger counter in there detecting whether it releases a quantum particle, radioactive particle, which will then break a vial of poisonous gas and kill the cat. Now, the decay of radioactive particles is a quantum behavior, and you don't know whether it decayed until you actually look to see if it's decayed. Kind of the same way we measured there to see which way the photon went. So as long as you're not measuring, the idea is that the radioactive particles in a state of both decay and non-decay, and until you open the box to measure which way it went, whether it decayed yet or not, the cat is also in a state of superposition between dead and alive. And so you open the box, and at that point, effectively, you're causing that measurement of saying, which way did that particle go in terms of decay? Kind of another way of looking at the double-slit quantum eraser experiment we just looked at. So what we've been talking about is something called superposition, and this is one of the powerful aspects of quantum computing, is being able to superimpose multiple states of information onto one bit. And if you take a look at a classical qubit on the left, a classical bit on the left, it's got a state of 0 or 1, just concretely 0 or 1. It's like a light bulb. When you take a look at a quantum bit or a qubit, it can live in a state of superposition where it's neither a 1 nor a 0. It's probabilistically one or the other. And the probability can vary. It can be 30% 0, 70% 1. And this is superposition and one of the, like I said, the key aspects of quantum computing. And here's the way that you describe that in mathematics and quantum computing kind of lingo, is to represent it as these state vectors. You see 0 and 1, that represents the state that the qubit is in 0, and the one that it's in a state of 1. And then you've got probability amplitudes. They're called probability amplitudes because you've got to square them to get the probability that it's in one of those two states. So you see alpha 0 and beta 1. The probability of it being in a state of 0 is a squared. Now, the true math behind this is those can be complex numbers, so they can be negative as well, and they can also be complex. And so when you square them, though, they end up becoming positive numbers of probability. And the total probability is always going to sum up to 1. So that is the core principle of quantum computing. And thus, this is my shirt. You probably get the joke now on my shirt. This is a cat that's alive, and that's a cat that's not alive. And then there's the probability amplitude, 1 over the square root of 2. You square that, and it's 1/2, which is 50%, and 50%. So this is Schrödinger's cat, represented as a quantum equation. Now, the thing is, like I said, superposition is one of the powerful aspects of quantum computing. And just to give you an idea of what you can do with it, let's say that you're searching for an answer. And this is a very famous algorithm called Grover's algorithm that I'm demonstrating here that uses superposition to come up with an answer quadratically faster than a classical algorithm can on standard computer. You're searching for an answer. There's a bunch of numbers. One of them is the number that you're looking for. And that's identified by some oracle that says this is the answer. If you take a look at a classical search algorithm, you're basically stuck with order n search, looking for that one number that is the number that is going to say, yeah, I'm the answer. That's an order n problem on a classical computer. But with a quantum computer, you put these into a state of superposition, and you magnify the state of the answer because it's got a special characteristic to it that identifies it as the answer. And what you do is you magnify it, the probability that when you measure the system, you're going to come up with 6. And that's order squared n in terms of the number of iterations you go through of taking that superposition, magnifying the one that has the answer in it, repeating that, and I'll show you that in a second. But that's an order square of n time to n answer, which is a quadratic speed up over the classical algorithm. And so this is one of the kind of key cornerstone breakthroughs in quantum algorithms, is Grover coming up with this way of doing search faster than you can in a classical computer, and showing classical computers could definitely do and solve problems faster than or quantum computers can solve problems faster than a classical computer. So let's take a quick look at Grover's algorithm in action on a quantum simulator. Uh-oh.
Thought you guys were passwordless already.
Yeah, we're supposed to be. Huh. Tashi, did you change the password on this? Or do I've got caps lock on, or what's going on? Let's try that. Now I'm locked out.
Sorry, this is the background machine.
Yeah, I didn't expect applause for that. Well, I don't know what I did. If only we had somebody that knew Windows. Here. Here, Control Shift. Oh.
They should lock you out.
Yeah. Okay, thanks for changing the password. That's Hashi, by the way. Okay, so where were we? Oh, yeah, this demo. So this is the Grover search algorithm in a quantum simulator, and you can see as I step into this, executing instructions, and this is going to visualize the state of the system. You can see the first thing it does is allocate 3 quantum bits or qubits. So when I step over that instruction, what it does is apply a special quantum gate called the Hadamard gate or H gate to put all of those qubits in a state of superposition, which means that if you take a look, the probability amplitudes of them are all the same, of those qubits, the states those qubits represent, and they represent 8 states because there's 3 qubits, so 2 to the third is 8 possibilities for when we measure. We can get one of 8 possibilities, and the possibility of getting any one of those 8 states is exactly the same. Now, what this simulator in this example is going to do is make the answer to one of those that 8th state. And we can see that it's magnified here. And now Grover's algorithm, what it does is going to flip this, the probability amplitudes. You can see they're negative here. But because we square the probability amplitudes to get the probability, it doesn't matter that they're negative. And that's the way that classical computing or quantum computing actually works. If we step over it again, the Grover's algorithm goes through multiple iterations to magnify the answer of that, basically magnifying the probability amplitude of the state that has the oracle saying this is the one that's the answer. I know that's a little hard to follow, but basically that algorithm right there, you can see how it's executing on top, magnifying that answer. And now, if we do a quantum measurement, when you do a quantum measurement, you collapse the state of the system from this superposition into it's either an answer of 0 or 1, basically. So those 3 qubits, when we measure, collapse into states of 0 or 1. Now, the chance that they'll collapse into a state of 1, 1, 1, there's 7, or the 8th bit, that is that high probability there, as represented by that probability amplitude. So that's effectively quantum computing, the basics of it, how measurements work and how computations work, is manipulating these probability amplitudes together. Then when you do a measurement, the system is said to collapse to an answer of one of the possibilities. And the possibility you get depends on these probability amplitudes. So let's take a look at another bizarre quantum property, and it's called entanglement. And this is used in quantum computing as well. And this one's potentially even more bizarre than the superposition property that we just took a look at. Einstein was so freaked out by this, he called it spooky action at a distance, and he actually didn't believe it was real. He thought that there was some underlying explanation for this behavior that we hadn't figured out. And the fact is that experiment after experiment has shown that what I'm about to tell you is really the way the universe works. There was an experiment done just a few years ago, which is believed to conclusively prove it. Basically, it's called the loophole-free Bell experiment. It was done in France, where they entangled 2 particles and did measurements on them and showed probabilistically that there's no way to explain it other than the fact that the universe behaves with this entanglement property. And so I think at this point, most of the physics community believes, yes, this is really the way it works. And so what is entanglement all about? Entanglement's about having 2 particles that's fates are attached to each other. And when I measure one, the other one collapses into a related, correlated state. But until I do a measurement, they're sitting in this state of superpositions that are related to each other. So imagine that I've got a ping pong ball, and I can paint it a mix of colors, and then send that 2 copies of it, basically, to different sides of the universe. There's a probability that I take the red one and the yellow one, combine them together, and then take the combined ping pong balls, split them apart, and send them to different parts of the universe. The entanglement property says that when I measure one, regardless of what I measure it at, whether it's red or yellow, the other one will be the opposite color. And until I actually do the measurement, they're in a state of kind of combined superposition where they're both red and yellow. So if we take a look, measure one, measure the other, we get that correlated effect. And this is a very simplistic view of entanglement. There's actually much more complicated entangled states. But the bottom line to remember about entanglement is the states of these things are correlated. And when I measure, it forces the other one to collapse into either a 0 or 1 based off of this one. If there's a 1/3 chance that this one's red, then, and a 2/3 chance that it's yellow, and I measure this one and it's red, the other one's going to be yellow. Just guaranteed. It's not going to be like I measure the other one and it's still 1/3, 2/3. It's going to come out with the answer as defined by whatever I measured on the other side. So that is the bizarre Einsteinian conundrum of entanglement. So let's talk a little bit about now that we've got the two kinds of basics of quantum computing behind us, which is superposition and entanglement, and let's start to take a look at how you build a quantum application in quantum computing and make use of this. We just announced at the keynote Microsoft Azure Quantum, and where Microsoft Azure Quantum is a comprehensive program that brings together companies that are doing software development kits for quantum computing, as well as companies that are doing hardware work on creating quantum computers and making that available through Azure. So, and this is going to launch in private preview in the next couple months. When you sign up, you'll have access to quantum computers, real quantum computers from a variety of different companies, and you'll have support for our SDKs, which I'll talk about more in a second, as well as the SDKs and computing tools of these other companies, all through Microsoft and through Azure. When you talk about building a quantum application using the toolkits we've got something called the QDK, or Quantum Development Kit. It's been downloaded 200,000 times, which means if you estimate that about 1% of people understand what they're doing with it, that there's about 2,000 people out there that are making good use of quantum computing on the QDK. But if you take a look at what's inside of it, there's a Q-sharp compiler, which is how you write the quantum code that will then get deployed onto the quantum computer itself. You have the classical host program. You could, for example, use C#, and that's what I'll be using in the examples, to drive the classical computer. And this is one of the also things that I want to highlight here, is that you can think of quantum computing as an accelerator for certain types of problems. It's not a replacement for classical computers. There's things that it can, theoretically, a quantum computer can do everything and more than a classical computer, but practically, it's extremely inefficient at lots of general purpose things that classical computers do a lot better. But for these kinds of problems that we've been talking about, you can uniquely do them on a quantum computer. So what you have is generally a host program that is doing all this stuff in classical, and then calling out to the accelerator like you would a GPU and saying, go do this part, which is the hard part for classical computers, and then come back with an answer, and I'll do some more processing on top of that. Also with the QDK, there's a bunch of algorithms, the growing list of algorithms libraries. And then when you deploy it, you can deploy it onto a classical runtime, which has a few different plugins. One's to simulate the quantum algorithm, basically pretend this is what would happen on a quantum computer, and just based off of probabilities, when you do a measurement, just say, oh, if there's a 30%, it's this, 70% is that. We'll use our classical random number generator to figure out which one it's going to be. And so you kind of simulate the behavior of the quantum computer. There's also a resource estimator. So as we get ready for real classical quantum computers, we need to know how complicated these algorithms are in terms of quantum hardware. And so built in that as well is how many quantum gates is this going to take? And there's to fully simulator, there's a set of 3 or 4 gates that are considered the universal gates. You can represent any quantum circuit using them. So if you want to get a true idea of the complexity of your algorithm, you use the Toffoli simulator. The resource estimator tells you, hey, if we were to use any gates, this is how complicated, how many gates of different types you'd need probably for this algorithm on a real quantum computer. And then finally, we're building a real quantum computer, and I'll get more into that in a little bit. But I want to show you what this QDK is like in practice, just by doing a very simple algorithm, and this is a quantum number generator. Remember I told you about that Hadamard gate. You can see that there's an H. We're taking a qubit that's in state 0, so 100% probability that it's 0, like a kind of a classical bit at that point. We're going to pass it through a Hadamard gate. The Hadamard gate's going to put it in a state of perfect superposition. 50% 0, 50% 1. So it's effectively the world's purest random number generator, really using quantum mechanics to put it into a random state if we had real qubits at our disposal. So you can't get any more random than this, because this is the fundamental randomness of the universe. So the best random number generators are quantum computers. Now, and then you can see here, there's the 1 plus 0. That's representing the probability amplitude that it's in a 0 state, which is 100%. And when we put it to the Hadamard gate, you get this equation that I've got on my shirt. And then you measure, and you've got a 50-50 chance. So let's go take a look at that in action in the QDK. So here's the Visual Studio. And I've got this driver. This driver is the classical part of it. And you can see it's just doing 10,000 runs, invoking the quantum simulator. And for each of these, for the quantum simulator, it's calling this run command, which calls into the Q-sharp portion, the quantum portion of the program. And it gets back a result, which it's just going to print out. If it's a 1, it's an X. If it's a 0, it's a dot. And if we take a look at the quantum part, here's the quantum part, which is just the Hadamard gate. We're going to have an assert Q-sharp statement that says, this is what I expect at this point in the program the probabilities to be. So just verify that it is using the simulator that's underneath. And then it's going to do this measurement. And one of the things about the measurement, you can see it's called M reset Z. M stands for measure. Reset says, hey, reset this qubit back to this state. And that's one of the things that I kind of talked about a little bit earlier. When you measure a quantum state, it collapses. And so you lose all the information about what was in that state. In that Grover algorithm, when we measure, we lose the probability amplitudes. So there's no way to directly get out of a quantum system what's the probabilities of it being in this state versus that state. The best you can do is simulate what it should be, or measure, and measure over and over. You put it back in that state, measure again. Put it back in that state, measure again. And then you can infer what the probabilities are just because you're getting results that match those probabilities. Does that make sense? So 30% chance it's in this state. I measure 3 times, and I get 1 time in that, 2 in the other. It about lines up. But there's no way for me to know for sure that it's 30%. So anyway, that's what this little program is doing. We're going to go ahead and run it and measure after we're in that state of superposition, and we should get 50-50. And this is using the simulator, so it's going to be simulating that state, that Hadamard state of 50-50 superposition, using the internal computer's random number generator. So you can see we see about 50-50 X's and dots, and then it says the probability of 1s was 48.93%, so pretty close to 50%. And this is what you would see on a real quantum computer, basically, because there's no guarantee, just because probabilities, that you're actually getting at 50%. You could have a bizarre run where it's all one way or the other, and that totally blows your estimates. One of the things you can do is use different kinds of gates to put the system in a different state of superposition. So I'm going to put it in using this phase rotation gate, put it in a state using this, and basically all the phases you do are on a circle. So you're using basically 2 pi kind of rotations, and that's where you see sine and cosine show up. So if we want to put it into a state that's different than 50-50, we've got to start using that kind of math. And so what we're doing here is putting it in a state where it's 30% one state, 33% one state, 66% the other state. So we'll run this again, and we should see the change. So this kind of shows you how you can use these quantum gates to put qubits in different states of superposition and then make use of it. So you can see probability of 1, 33% that time. So that's a little bit of a hello world. And you kind of have seen a hint of the kinds of gates that we're talking about here. There's, underneath the gates, you're dealing with matrix algebra. So this is, if you're familiar with machine learning and all the matrices, tensors that you're dealing with there, quantum computing is built on top of the same math. If you take a look at the way that you represent a 0 or 1, 0 is kind of the left column and a 1 is the right column. And then you're setting up probability amplitudes based off of that. And so when you take a look at the identity matrix, you're taking a qubit that's in some state, you're multiplying it by this matrix, you're going to get the exact same state. So if you take a vector that has a 0 on top and a 1 on bottom, you multiply it by this matrix, you're going to get a 0 on top, a 1 on the bottom. So if you're not familiar with matrix math, no big deal, but for those of you that are, that's the way that you're doing quantum calculations on quantum states. And so these different states allow you to manipulate the phases and effectively the probability amplitudes of the different states that are represented in qubits. And those are single qubit gates. There's multi-qubit gates. And the most famous is a C0 gate, a controlled NOT gate. That's the way the matrix looks, basically, and that's the representation for it in quantum circuits. That circle at the top, the dark circle, says, based off of the value of this qubit, either not the other gate, the other qubit, or leave it alone. If this qubit is a 1, then flip the state of the other one from a 0 to 1 or a 1 to 0, otherwise leave it alone. And that's the way that it behaves classically. In a quantum world, because that top bit can be 50% 0, 50% 1, you're kind of messing with the other qubit at that point and putting it into a 50-50 state as well. And what you've just done is entangled those two bits together. So this gate right here is the fundamental gate for entangling two qubits together, because the state of the bottom qubit after you execute this directly is related to the state of the top one. Again, if the top one's in a superposition, and the common way to put it in a superposition is to put a Hadamard gate. Now it's 50-50. Now put it in a controlled, have it be the control bit for a controlled NOT. And now that other bit is also now entangled with that 50-50 superposition. And that's called a Bell state. And you're going to see that over and over again as you get into quantum computing, is that same pattern in circuits of entangling bits together. In fact, here's a sample quantum circuit. This one is for something called quantum teleportation. And quantum teleportation sounds like, Star Trek, science fiction. Yeah, we're almost there. Unfortunately, it's not that. Here's what it is. What quantum teleportation really means is, I've told you that you can't see inside of a quantum system. And when you measure a quantum system, it collapses, and you don't know what the original state was. You just get some probability outcome. So, and one of the other key aspects of quantum mechanics is that you can't copy a quantum particle's state. There's no way to copy it, because you can't see inside of it, you can't copy it. What you can do, though, is transfer it from one particle to another. In the process of transferring it, though, you destroy the state of the original one, and you collapse it. But you can move the state to another particle. And that's called quantum teleportation, taking the state of one particle and transferring it to another one. And that sounds really kind of cool, because that is kind of teleportation of the state. Like, we're all built of basically quantum particles. If we could take a random set of particles standing next to me and transfer my state into that, I've teleported. Now, the challenge is, though, that for me to figure out now for me to do the final step of the teleportation, I need to actually perform some quantum gates on that final teleported version of me, based off of measurements that I do off the original version. So I'll destroy the original version. I'll get some information out of it. Okay. I think this happened last year, too. So I thought, I don't know, somebody's mind was blown and we need to evacuate the building. Yeah, Amber Alert, yeah. So I'll just speak over it if you don't mind, because I don't know how long this will go. But So as I was saying, we're teleporting my state from me to another version of me. I'm destroying the original copy of me to get some information that then I need to use to go and do a final manipulation of the state of the transported me. And that information I've got to take, and it's classical information. It's like 0 or 1, which gate do I perform on this state of me over here? I've got to get it over there somehow. So I can't do that any faster than light. Einsteinian physics says I've got to move it across the universe at less than the speed of light. So yes, I can teleport my quantum state. I'll destroy the original version of me. I hope that the classical information makes it over there safely, because if not, I'm not showing up on the other side. But that information is going over there classically. And you can see that is represented in this quantum circuit right here. You can see that Bell state entanglement that I just told you about show up twice in this. We've got that top quantum state, alpha 0, beta 1, state of superposition. I want to send that down to that bottom qubit. And but I'm using this qubit in the middle to entangle states together. And the first thing I'll do is entangle the bottom qubit with the middle qubit using that Hadamard gate plus the controlled knot. Then I'll entangle that with the top qubit using another controlled knot. I'll use a Hadamard gate. Then I do those measurements on those 2 top qubits. Based off of those results, whether they're 0s or 1s, I then choose to use these controlled gates down there. Basically, again, that's a controlled X gate, which is a knot. And if that's a 0, then it'll flip the state. If it's not, it's a 1. So basically, that's the classical information I'd have to send, is those results of those measurements. Those dials are measuring. Is it a 0 or 1? And probabilistically, it's going to come out one or the other based off of the state of superposition. So that is quantum entanglement. And let me show you that in a quantum simulator. Now this, I'm really excited to say, is a brand new quantum simulator. It's called Bono. And Hashi's the one that wrote it. Hashi, who you just saw come up here and save my demo. This is Hashi's Bono quantum simulator. It's graphical, and it's kind of cool. So what I can do is do that same thing that I showed you before, put the Hadamard gate there, and then do a sample, which lets us real-time sample. Basically, the Bono system is just constantly doing measurements according to the probabilities and telling you whether it's a 0 or 1. As you can see, it's about 50% 0, 0, and 0, 1. It'll also show you, with this yellow bar, the state of the system here. And you can see that's perfect superposition. This is one way of looking at superposition, a different way than that alpha beta way that we just showed you. This is using circles. The more filled in they are, the higher the probability that's in that state. And then that arrow is kind of the phase, which says if it's negative or positive, effectively. And that's where you get interference. So this is a growing set of samples that we've got loaded into Bono. And there's quantum teleportation right there. And what I'm going to do, this is a cool thing about Bono, is that it's got this circuit editor that shows you the equivalent Q-sharp code. And you can take that Q-sharp code and drop it into Jupyter Notebook service on the quantum QDK. So this is something else we've got, is a Jupyter Notebook service as part of the quantum development kit. And then I can run that in the simulator. And then I can teleport some random message. And then show that I sent this state and I received that state using teleportation. So that's something to check out. And now Bono is open source. Here's the GitHub repo for it. And what I'm going to do right here is, you can see it's at Microsoft/Bono. I'm going to make this GitHub repo public right here to kind of announce it to the world. And, oh, OK. Anyway, I'll do it later. OK, so let's talk about some other quantum algorithms and some different applications for quantum computing. The first one I'm going to show you is something that, again, shows one possible application of quantum computing, which is to generate secure keys in a way that's much more secure than any way we can do with classical computers. This is not the state-of-the-art algorithm, but this one is simple enough to explain and to kind of get the idea for how secure key generation works in a quantum world. Now, one of the goals of generating a secure key and sharing it with somebody else is you don't want somebody to intercept it on the way. And what quantum computing lets you do is identify if somebody's snooping. Again, remember that principle of if I want to see the state of a quantum system, I have to measure it. In the process of measuring it, I destroy information. And I cannot get that information back. All I've done is measure and get some probability of it being in one state or the other. That's what this algorithm takes advantage of. It's the BB84 protocol. You can guess what year probably it came out. Now, the basics of this are that we can do measurements using what are called different bases. And these different bases determine, basically, if you have a 0 or 1, 1 is vertical, 0 is horizontal. Or sorry, 0 is up, 1 is down. If I measure in the vertical basis, I'll measure a 0 and a 1. If you give me a 0, 1, I'll measure a 0, 1. I can also measure in the horizontal basis. If I measure in the horizontal basis and you give me a 0, 1, I can't tell the difference. I'll get randomly a 0, 1. You have to measure in the same basis as me for you to get the value that I want to give you. So if I want to give you a 0, we have to agree on the basis. Let's both agree on vertical. That means when I give you a 0, that's up. And when you measure, you're going to see an up. So we're going to use a 0 as vertical and a 1 as horizontal. And when I send you bits, I'm going to send you them up or to the right. And for you to measure the bits that I'm sending you, you've got to pick the same ones. But here's the thing. I pick random ones to send you. So I'm picking random 0 or 1 string. Now you're picking a random basis, either vertical or horizontal, to measure at the same time. So you do your measurements, or Bob does. Bob picks a random set of bases, vertical or horizontal, and measures. If Bob picked the same basis as Alice, Bob is going to get the same value that Alice transmitted. If Bob picked a different one, then Bob's going to get a different answer. And we don't know exactly what answer Bob's going to get. It's going to be 50-50, like I said. So you can see those ones in the middle there that aren't circled. That's where Bob picked a different basis, and who knows what Bob's going to get, a 0 or 1. Certainly not a guarantee that they're going to get what Alice sent. Maybe or maybe not. So at this point, what Bob and Alice do, so Alice has created the string of bits, sent them. Now Bob picks bases, measures the bits. Now Bob tells Alice, and Alice tells Bob which bases they used for all of their bits. So that way they know exactly where they matched and where they didn't. So this is public information. And what they do at that point is they take half of the bits that match, where they matched, and say, hey, did you send a 1? Because I got a 1. And if they did, and they see no discrepancies, then there's an extremely high confidence that nobody was snooping. And they can use the other half, those bits, as their key. So in this case, the key would be 1 and 1. What would happen if Eve was trying to intercept their key exchange? So let's take that same thing, except Eve is now there. Now Eve doesn't know the bases that Alice is sending. Eve just has to pick random ones too, just like Bob would. And now Eve has picked some wrong ones. So those wrong ones are red, and for those, Eve gets either a 0 or 1. No guarantee that they got whatever Alice sent. Now Eve forwards those measurements along to Bob. So Bob does his measurements, and some of those are going to match what Alice did, and some of them aren't. So they take the ones that matched and compare their values, and they say, whoops, you know what? Because Eve measured and collapsed that second highlighted blue, there on the top got a wrong answer because Eve measured in a different basis, and so they got a 1 instead of a 0. And they passed that along to Bob, and Bob goes, wait a minute, we had the same basis here. You sent a 0, but I got a 1. Something's fishy here. Eve must be in the middle. So then they throw away that key generation, and they try again. Or they come up with some other way to exchange the information. But that's the basics of secure key exchange, which kind of leads us into cryptography in general. And one of the big scary things about quantum computing is this right here, cracking RSA. This challenge, it's called the RSA 7068 challenge problem, which was to take a 768-bit RSA key and crack it. And this was successfully cracked. So there was various iterations of this problem, starting with smaller and smaller keys. Back in 2008, in 1991, there was a 100-bit RSA key that was cracked. This 768-bit key was cracked in 2009, and it took the equivalent of 2,000 years of computer time to crash. They did it in 2 years because they had 1,000x parallelism, but it took a huge amount of time, but they were able to crack this 768 key. Now, what length key are we using today? Generally, what's the recommendation? 2048. So 2048, basically there's a new challenge, 2048. So how long do we think it would take on a classical computer to crack this? Basically, cracking this is factoring a very, very large number, 2048-bit number, and factoring it into primes. How long would this take on a classical computer? Using the fastest computers we have today, that long. So really, this is why people are like, yeah, 2048 bits, that should get us by for a while. But along comes quantum computers. How long would it take a quantum computer of sufficient size to crack 2048-bit encryption? About a minute and a half. And this is kind of the scary thing for a lot of people about quantum computing is, in fact, most of the time when I say I'm going to give a talk on quantum computing, they're like, oh, you're going to talk about breaking cryptography. I'm like, no, that's not the point. That's kind of a side effect, but that's not what we're going after here. And the way that this is solved is a scientist, a researcher named Shor at MIT, came up with this way to use quantum computers to basically estimate a number that is likely to be one of the prime factors for one of these large, very long numbers, and use a quantum computer to help guess that number. The algorithm is a little bit complicated, surprise, but basically you start with a guess of a large number that's less than n, and then you use this quantum algorithm to estimate a phase of the large number n, and then use that phase to come up with a better guess based off of the one that you just came up with. So you can see that equation at the bottom. Instead of using g, you use g to the phase over 2 plus or minus 1, and you say, hey, maybe that's the right answer. And you start iterating off of that number, looking for a prime number that's close to that. And so that's where you get to that multiple step of iterations to hopefully come up with the prime, one of those two primes, to factor that number. And this is called a quantum Fourier transfer, or QFT algorithm that Shor came up with to estimate that phase. And that is the secret sauce, and that is what quantum computers are really good at. If you imagine superpositions and destructive and constructive interference, that's what Shor's algorithm takes advantage of to get the system into a state where when they do a measurement that you are likely to get the right answer of lots of constructive interference showing you what the phase is. So let's see that in action. We're going to go crack a prime number open using the QDK. And so this is Shor's algorithm in Q#, factor integer, right there. And what I'm going to show is it's going to try to factor 15. And it's going to take guesses, and it's going to iterate, and it's going to get some of them wrong. But it's using Shor's algorithm underneath. And so if this was on a classical computer, you can see even factoring 15 on a classical computer is extremely slow when you're doing it using a blind factorization algorithm and not just doing a brute force search. It's going to take a while. And sometimes you need to start the thing over. Well, this is going to take a second. But while that's running, I want to show you something else. And sometimes this finishes fast. Sometimes it takes longer. So, yeah, and we're having bad luck with Shor's algorithm today. But bottom line is, this is the algorithm. It's part of the Q# SDK, so you can go look at it. One of the reasons why it's so hard to simulate a quantum computer is the amount of memory required to model the states that it's in. And this is why you can only model a quantum computer up to a certain size on top of a classical computer. I've got this little program right here. All it does is allocate qubits. So for 1 to 36, I'm going to try to allocate qubits from the quantum simulator. For each qubit that I add, I 2 to the n grow the amount of states it's got to keep track of. Because remember, when I had 3 qubits, that's 8 potential states, each with their own probabilities. So the quantum simulator needs to keep track of each one of those different probabilities. So when I run this, you're going to see how much RAM the simulator consumes to try to keep track of all the states of all the qubits. 26 qubits is 1 gig, 27 qubits. 28 qubits is 4 gig. So this is why it's so hard to do these kinds of problems that on a quantum computer are trivial, is because of that. And then we just crashed, ran out of memory. You can see system runtime exception. And where did we bottom out? We bottomed out at 8 gig at 29 qubits. So that's fundamentally why it's so hard to simulate a classical algorithm like quantum algorithm, why quantum computers are so good at what they're doing, because they store so much information efficiently. How many qubits does it take to solve, do we estimate? 2048-bit and break 2048-bit encryption? About 2,000 qubits. And I'm going to talk a little bit more about what that means in a second. But the timeline for this, because we need to start getting ready for this, because it's not a matter of if, it's a matter of when this is going to happen. Nobody knows exactly when. There's a lot of breakthroughs that still have to be done to get to a scalable classical computer that can be that large and solve that kind of problem. But we're estimating at Microsoft, we're shooting for 2030 as our target for this. And kind of the rest of the scientific world, cryptography world and quantum world agrees with this assessment of roughly then we need to be ready in general computing to deal with this problem as it shows up and these keys can be cracked. So we're here, you can see, close to 2010. There's been a ton of R&D going on. We've got pilots now in flight for different algorithms. And we're going to start rolling out new post-quantum cryptographic algorithms, or PQC, post-quantum cryptographic, yeah, PQC, algorithms in the next year to 2 years, and start rolling those out across our software products, decommissioning the old algorithms like RSA, and migrating our systems to these new algorithms. And hopefully the world will be ready. This will be kind of the Y2K for Y2030, I think, situation. And then all along, there's been standards discussions, because we all need to agree about what kind of algorithms we're going to use. So we're all speaking the same language, and we all agree on the strength of these algorithms. So NIST, a few years ago, had a post-quantum standardization project, launched it as a contest. inviting submissions for encryption algorithms and for signature algorithms that would be resistant to quantum computers. And it launched UC 2017. There's about 70 submissions. 6 of them have already been withdrawn. 9 have been succumbed to attacks on them. Microsoft submitted 4, 2 in the encryption category, 2 in the signature category. Both of them have made it through. In round 2 was announced in late January 2019. 26 algorithms advanced from that original 70 into round 2, including all 4 of Microsoft's algorithms. So while we're working on quantum computing on one hand and kind of being part of the problem, we're also working on this other side to be the answer to the problem for you too. And then the quantum team has been working with a consortium, the Open Quantum Safe Project, to make quantum algorithms available early so we can start testing them, like integrating them with things like OpenSSL and OpenSSH. And they've even set up this PQ VPN project, which is a VPN gateway with post-quantum cryptographic algorithms on it. You know, you think that these guys, wow, they're really into security. Look at this, how they're trying to help secure the world. And then I look at the top of this thing, and then I'm like, OK, you're great physicists and mathematicians. So we're already working on that side of things as well. Now let's talk a little bit about building a quantum computer, because we've talked a lot about the theory of quantum computing and mechanics and these SDKs and these different tools. And by the way, our Q# SDK and QDK is not the only one. There's a bunch of others out there. But you need real quantum hardware to build these things, to actually run these things on. You can't use simulators. So what does it take? This is what it takes to build a quantum computer. And when you step back and think about it, you know, having a few qubits, doing a few simple operations, that doesn't cut it. You need a whole top-to-bottom system. You need a general-purpose quantum computer. And these are kind of the characteristics that we set in front of ourselves as we go after building a quantum computer. It needs to scale. You need to be able to easily reset it. It needs to be extremely stable. And one of the challenges with qubits, as we'll talk about, is that their quantum states are very fragile. They can effectively be measured by random interference. And once you measure, you're done with them. Like they've lost all their interesting state for algorithms. And that's a process called decoherence. So the computers need to keep the qubits extremely stable. They need to be measurable. So you need, at any point in time, be able to say, let me measure this qubit state. And you need to be able to get data into it and data out of it. So converting data to put in the quantum computer and then extracting the results out of the quantum computer. And this is, so when you just take a look at how can we just put together some qubits and do some measurements off top of it, that's just a tiny fraction of the overall problem. Which takes us to, what is a qubit in the real world? Well, there's different types of qubits. The qubits we've been talking about so far are kind of the perfect qubits. When I say 170 qubits to solve the nitrogenase problem, that is assuming you've got perfect qubits that never decohere. You can do computations on them for seconds, minutes, hours. When you do probability measurements on them, you're going to get back really the probabilities of those true quantum states. But that doesn't exist in the real world for us to be able to harness. We can't have pure theoretical qubits because the real world interferes and causes qubits to decohere. So what we've really been talking about are logical qubits. Logical qubits are ones that we can build ourselves and that do have very low error rates, low enough that we can actually solve real problems on top of them and have high confidence that the answers are valid. Now, logical qubits, though, there's no such thing as a very low error rate qubit physically that we can use. The real qubits look like this. These are physical qubits that we've got in the real world today. And so what is a real qubit? What is a physical qubit then? A physical qubit, there's lots of different objects that exhibit quantum effects. Once you start to get down into the quantum scales, like an atom, even molecules, you start to see quantum effects of superposition and entanglement. So there's lots of different ways to build a qubit. And here's a slide of some of the types of qubits people are building out there. There's silicon photonics. There's so those are using photons of different polarization. There's superconducting qubits. This is the most popular out there. So IBM, Google are going after superconducting qubits. There's quantum dots or spin qubits. These are taking advantage of the spin of quantum particles like electrons, so they can spin up, down, left, right. There's trapped ions. So this is taking the states, energy states of atoms, and then trapping them in high field magnetic fields, high energy magnetic fields, or trapping them with lasers. And then there's topological qubit, and that's the one that we're going after. Each one of these qubits has different characteristics in terms of its stability, different characteristics in terms of how much complexity there is to actually make one. Like when you start talking about lasers, you need lots of lasers for lots of qubits to keep them in their trapped ion states. And so each one has pros and cons. When you take a look at the error rates that we see with the qubits that we've got today in the real world, physical qubits, we see error rates that are up on the right side of that graph right there, up into the 10 to minus 3, that x-axis. And one of the goals of logical qubits is to have an error rate that is in the 10 to the minus 12th range, because only with qubits with that low of error rate can you actually do a real kinds of quantum computation. And so you can see the number of physical qubits with error correction you need at a certain error rate of that physical qubit to achieve those low error rates that you want for a logical qubit that you do computation on. If you've got error rates of 10 to the minus 3, you need hundreds to thousands. If you have error rates that are farther to the left, you start to get down into the 50 to 100 range. So the qubits that you see people using, including Google and IBM, they're called noisy intermediate scale quantum qubits, NISQ. And they're called that because they've got very high error rates. They need a tremendous amount of error correction, hundreds of physical qubits to create a logical qubit. The qubit that we're going after, the topological qubit, we believe needs on the order of hundreds, low hundreds, dozens, maybe, physical qubits to create a logical qubit. Further, we also believe that the topological qubit structure allows us to be much more compact than is possible with these other types of qubits. And so that is the bet that we've been making, is these topological qubits. So this is an example of the kind of circuit that we're creating. You create a nanowire, and you induce the existence of a quasi-particle called a Meyer and a fermion, which exists in two places, effectively, at two ends of that nanowire. And you can put those in states of superposition, basically, these Meyer and a fermions. Now, Meyer and a fermions were theorized to exist back in the 1930s. We believe we've got evidence that we've been able to create one, and now what we're doing is building them up into real qubits that we can control, and then qubit quantum gates on top of that. The really powerful thing about topological qubits is that you can take these pairs of Meyer fermions and you can put them next to each other, and what they create, those connections between the two halves of them, are what are called braids. And the more you have together, you can see there's 6 here, the stronger they get, the more resistant to interference they become, because they reinforce each other. You can see these two examples, pictures, that have different braid structures. That's why they're called topological. They are the same value. So they can be interfered with heat and light and magnetic fields and still maintain their values. So they've got a much higher stability, orders of magnitude, over other types of qubits like the semiconducting qubits. We're at Microsoft working on building a true scalable quantum computer off of topological qubits. You saw in the keynote, there's 8 labs around the world, including one at Microsoft's campus, where we're building quantum computers. And it's taking researchers, academic researchers working with Microsoft researchers together on building it. And I thought I'd show you some pictures. This is the zoomed out view of a materials growth chamber. This is where we're actually using something called selective area growth to create semiconductor, superconductor materials that lay on top of each other to create the environment where we can create these Majorana fermions. Just to show you that quantum scientists have a sense of humor, this is one of the things they've got in that. So I thought it was pretty funny when we came across that. Now, this is what you're looking at is what we use to build the materials of the quantum processor. One of the things that we need to do to get rid of noise is operate these things at extremely low temperatures, in the low millikelvins. And we use these dilution fridges to take liquid helium all the way down to low millikelvins of temperature. Liquid nitrogen at the top, liquid helium at the bottom. And that creates this low millikelvin, which is colder than the coldest of space environment for those qubits to operate so that they're not being interfered with. Here's Rich Rouse. He's working on a probe that holds the quantum computer. He's actually looking for Jeffrey's fan base right there. Jeffrey Snover. Don't tell him I said that. Now, one of the things, if you take a look, every company, startup, major corporation that's going after quantum computers using dilution fridges like that. And one of the things they need to do is get control wires down into the quantum processor. And you can see the kind of hundreds of control wires needed to control the quantum processor at the bottom. This is what the general industry is doing. Now, we at Microsoft had just made a breakthrough very recently of being able to reduce that complexity and be able to control the quantum computer with just 3 wires. Not just, and so those hundreds of wires you saw control about 100 qubits. These 3 wires we can use using this cryogenically cooled CMOS processor on the left, which is controlling the quantum processor on the right. 3 wires will allow us to control up to 50,000 qubits. And the reason I'm pointing this out is that this is another example of the scalability challenges of getting to a true quantum computer that we're thinking through from top to bottom. Because if you've got a 50,000 qubit quantum computer, you can't have 50,000 wires coming out of that dilution fridge. So this is a kind of a breakthrough that we're really excited about that we just made at our station in Australia. And finally, I want to just talk a little bit about quantum-inspired optimization, which you heard about in the keynote. This is how we can take quantum today and leverage quantum effects to kind of inspire us to solve optimization problems on classical computers in ways that we couldn't before. And the math is obviously going to be very complicated, but this is kind of the standard that you see with optimization, where you've got a global maxima that you see on the right, and you might land in the wrong place in your optimization search for an answer. It's a local optima. You want to get to a better one, and there's the global optima. With a quantum-inspired algorithm, instead of taking the long route, you use basically tricks that are kind of like quantum tunneling to go from one low-energy state to another one until you get to the global optima. And this is real. So we've got a team of algorithmic researchers that work on quantum algorithms, but then they take their kind of inspirations from that out into a bunch of different industries that we see this applying to, and you can see a bunch of them here. The one that was mentioned in the keynote, of course, is Case Western Reserve, using this quantum-inspired optimization algorithm to reduce the number of MRI measurements by 3x. So you can use it in 2 ways. You can either get 3x the resolution, or you can speed up the time to get an answer by 3x. And they're using the time aspect to save money. Potentially, it's going to be tens of billions of dollars worldwide in savings of MRI machinery use using this kind of an optimization algorithm. And the other one that we're already seeing practical application for is in traffic optimization, which is a huge problem everywhere, including Seattle. It's getting worse and worse. But how could we leverage quantum algorithms and quantum-inspired algorithms to better route traffic? So this is a comparison of the different iterations we've taken on this path. You can see that we used a D-Wave, which is an optimization quantum computer that's commercially available. We were able to solve this route problem. You can see there on the left, that's the number of cars, number of unique routes, and number of route options. We're now down on version 3 there, or version 2 there, that you can see 5,000 cars, 5,000 unique routes with 10 route options. we're able to solve that problem using a quantum-inspired algorithm in a fraction of a second, which used to take minutes on kind of even a quantum computer. So we were able to do that in just a fraction of a second on a classical computer. And I've got one last thing to show you, which is just a live demonstration of one of those algorithms. And Hashi, the machine's locked again, and you haven't told me the password, so I don't know where you are. So everybody welcome Hashi back to the stage, Mr. Bono. Now, while he's getting that set up, I want to talk about one last thing. Reach under your chair. You may find a packet of polarized film. Inside, there's 3 sheets, 3 squares of polarized film. How many people did not get one? Sorry, that's the probability distribution at work. Now, if you didn't get one, we're going to be handing out some more at the door, so everybody should hopefully get one. Now, what you're going to do with these things, you can't use them yet because they've got protective films on them you need to peel off very carefully, but I've got an example of this up here to show you where you can see the quantum eraser experiment in action, where if I take the film and put them at this, they're polarized, so if I take one and rotate one and move it into a horizontal position, you can see that a lot less light comes through. And that is effectively measuring which way the light's going to go. But when I take another piece of film and I put it over at 45 degrees, I don't know if that's visible, the light starts to come through again. And that's erasing the which way information. So that is the quantum effect, quantum eraser effect. And I'm not sure I'm getting this in action. But if I take that out, the light disappears. If I put it back, the light appears. So it's kind of counterintuitive that I can put it in an extra piece of film, and the light actually shines through again. And that's the quantum eraser in action. So you can do that with your own piece of polarizer. All right, last thing is just to run this little demo here. Thank you. And so when I run the optimization, this is the vehicle scheduling optimization, which is using that quantum-inspired algorithm to converge on an optimal solution. And this is an example of quantum-inspired algorithms in effect that we're applying for real-world use. So I just wanted to show you that as a real quick demo. And then, lastly, leave you with, if you're interested in further explorations of quantum, of course, the Quantum SDK and QDK, go check it out. But I'm, like I said, I've become really kind of obsessed with this, and so I've read probably a couple dozen books on quantum mechanics and quantum computing. And I thought I'd share with you, I think, if you had just to pick 3 books, these are the ones that I would recommend. How to Teach Quantum Physics to Your Dog. So this is kind of a fun book, but it kind of is a great introduction to the quantum mechanics like superposition that and the Bell state that I just talked about. Then there's Quantum Physics, What Everyone Needs to Know. It's kind of the next step up on quantum physics, a really accessible book. And then finally, Quantum Computing for Everyone, which is from a real quantum computer scientist, one that does it as their job in research, and wrote a book to be as accessible as possible. So there's some matrix math in it, but it's relatively simple, and he explains it pretty well. So without getting into he actually avoids complex numbers, which is amazing altogether, because that's a true part of real quantum computing. But another great step into quantum computing. So with that, I want to thank you very much. I hope you found this useful, and I hope it blew your minds.